Okay, I think we'll just start with the introductions about news. I hope you had a good cheese and wine. It looks like some people had more wine than cheese. They didn't come back, but we'll see. Hopefully they'll join us later. One information about this morning is we're going to do a photo at the beginning of the coffee session. So you will be reminded, but don't forget we want to first take the photo in front of the building, and then we'll have coffee. Yeah? And yes, I'm very happy to have Saulius Grazulis here, who I met for the first time last year, but some of you probably know him or his work. He's one of the main maintainers of the largest open database for crystallography. So very important database. I don't know how, it's almost like half the size of the biggest commercial ones, I think. Yeah, 1/3, yeah. So very important, and we're very lucky that he accepted to come. And we already had a first session on Monday, and now we're happy to hear the follow-on. And he's from Vilnius, but I think he'll tell us more about that. A professor with a huge experience in software and bio and life sciences, I'd say.
Okay, thank you, Andy, for this very kind introduction, and good morning, everybody. Nice to see so many of you after yesterday's poster session, and it's a great pleasure to be here and a great honor to show you some of our work. The outline of my talk will be as follows. I will tell you a little bit about the crystallography open database, the COD, the COD, or COD as we sometimes say it, history, and this will explain the motivation behind the creation of this database. I will describe the contents of the crystallography open database and how to get it, and I will tell you how a little bit about the software that we use for maintaining and creating the crystallography open database. These slides are available on our archive, so you are welcome to download them, and all the references there are clickable, so you can follow them. I will start with some philosophical statement. In my view, crystallographic data are enormously important because they have a huge predictive power. In fact, any observations, be it powder patterns, measured properties, or even computed properties and scattering intensities, of course, must be compatible with the atomic positions and other parameters in our crystallographic model. If they are not, then something is wrong. Either our model is wrong, the crystal structure is wrong, or the measurement is wrong. It therefore would be extremely helpful if we could have all crystal structures collected in an organized fashion and available openly for all of us. This would make easier or even enable a lot of things useful for everyone, such as drug design, material discovery, teaching, citizen science, machine learning nowadays, of course, and many other things just limited by our fantasy. And in the field of macromolecular crystallography, this is indeed the case. The Protein Data Bank does an excellent job in making all macromolecular structure data freely and publicly available. In the chemical crystallography, the situation was, or still is, to some extent, somewhat different. There are certain databases for quite a while, but most of all, until recently, had a restrictive license put on the data that you get from them. This is a recent quotation from the CCCD terms of use. And not only the original data cannot be redistributed, but also the results that you derive from this data sometimes are not allowed to be distributed openly, as is exemplified by this quotation by Baldi in 2011 below. So a number of crystallographers considered this situation to be suboptimal, and back in 2003, a group of researchers from France, Spain, United States, Germany came together and Michael Berndt put this 3-step manifesto on how one could establish an open crystallography database. Okay, and this is the motivation behind it. Basically, we need, of course, collaboration and support from the community. We can benefit from open source software, and a team of engaged scientists can then do the thing. And 20 years after that, we have a site which many of you are familiar with. This is crystallography database, where we managed to do just what Michael Berndt envisaged. Okay, the project, the database appeared soon after the manifesto was written, so it's online for more than 20 years now. We have more than 500,000 structures available under CC0 license. The extent of crystallography open database is experimental, inorganic, organic, metal organic, and element organic crystal structures. We do not work with macromolecular crystal structures because these are, as I've mentioned, perfectly distributed by the PDB. And all the records are presented in standardized machine-readable form, which is documented in our original papers. The sources of data to the crystallography open database are, first of all, peer-reviewed publications from scientific journals. We take supplementary material there, and if it contains crystal structure data, we extract coordinates from there and convert it to the standard form as in crystallography open database is required. We also scan some preprints and dissertations, although not very thoroughly. Some data are deposited to our database directly by crystallographers themselves. There is an online deposition system, and we are very happy that some other databases are forwarding data to the crystallography open database, most notably the American Mineralogist Crystal Structure Database, initiated and maintained by Robert Downs in the United States. They also forward data to our collection. I must also mention, it's not on this slide, but there was another database called Crystal Eye, set up by Peter Murray-Rust and his PhD student Nick Day, who were doing a similar initiative and collecting published crystallographic data and chemical data. They were in the Faculty of Chemistry in Cambridge, so they were interested in chemistry, and they had at that time a comparable collection of crystallographic data, and when their servers were retired, they donated their data and we merged into the crystallography open database. So in this way we ensure the continuity of the existing efforts so that data are not lost. And both Robert Downs and Peter Murray-Rust are on the advisory board of the crystallography open database, so they can oversee that their data are presented correctly. One of the enabling elements that made crystallography open database possible is the crystallographic interchange framework. This is a standard maintained by the International Union of Crystallography, now into its second version, and it's very well suited for data publishing and archiving. It's a text-based, extensible, self-describing format. And this means that most of crystallographic data nowadays are already born digital in the correct format, so we can automate a lot of work that is needed for the ingestion of data into the crystallography database, and we can use the same format to disseminate data because most, if not all, chemical and crystallographic software supports it. You can access crystallography open database in many different ways. So starting from the simple HTML URI link, where for every structure which is identified by a stable, unique 7-digit code identifier, you can access a landing page where you see a picture of the structure and some essential data. You can get machine-readable data by accessing our custom REST endpoints. in the crystallography open database. If you again know the COD ID of the structure, then you get the data directly, or you can run a search using a simple query interface. We also implement a new standard for material science data exchange called Optimate. This is the first publication, and now is the second one coming out. This standard defines the REST interface for material science databases, which some 20 databases probably by now implement, including Materials Cloud, Material Genome Project, many others, okay? And we also implement that interface. The benefit of this interface is that it's very well documented, even though documentation is quite complicated, but it's well standardized. It's meant to be stable over revisions, so what you do now you will be able to repeat in the future, and it's supported by many different databases so that the query which you run on the COD can be run on Materials Project, and you will get the same structures from there. These will be theoretical, ours will be experimental. You can start comparing them. We provide open access to our SQL port because it's standard and SQL is immensely powerful. So if you know SQL, you can do queries of large complexity. If you use COD Reader as a username, then you are allowed to run select queries without a password. So far, no problems. I've managed to convince our computer security department that this is okay. And finally, you can download the whole database using Subversion protocol or our sync protocol, and I will show you a little bit on this later. And this is described in our documentation on the wiki page. We also reuse the methodology and code which was originally created for the crystallography open database, so for some other projects. So there is a constellation of sister databases. Probably the most interesting for you could be a theoretical crystallography, crystal structure open database that has DFT refined structures as opposed to experimental ones in the COD. Then there is an MPOD, material property open database, maintained by the Mexico team that has measured properties, pretty difficult to come by and to digitize, so not too many records, but very useful. PCOD contains predicted structures from some Monte Carlo simulations, from software of Armel Labai and his colleagues. And finally, we applied the same methodology to ROD to expose Raman spectra data, both measured and theoretical. And, well, slightly over 1,000 entries is not much, but it's not the smallest database either. Because, again, it seems that Raman spectra are not so easy to collect and disseminate. Okay, this is how the number of records grows in the crystallography open database. It's a little bit worrying that the growth rate has diminished, and this has to do with constantly changing interfaces with journals and changing publication styles. Maybe a little bit of policies involved in there as well. But I hope that we know the reasons and this can be remedied so we can have high growth this year. Now, when data come into the crystallography open database, it's not just simply stored there, it undergoes constant curation because our world is not ideal, so some data may be not in the ideal shapes, some data items might be missing, and this is an example of the data curation event so that you have a feeling what we are doing and how we are doing. First of all changes that we do to data are meticulously recorded in a version control system, and it turns out that version control systems like Subversion or Git that programmers regularly use for managing code are very well suited for managing scientific data as well. especially when the data are in text form as they are in the CIF files. So if you look what happened between the two revisions for this particular crystallography open database record, you will see that we added two extra data items, and the reason was that our upstream had a very peculiar convention for naming atoms. So WAT atom is not a tungsten, it's water. And we know this from cooperating with the upstream and from reading the original paper, but no standard CIF software can infer this. So we add this atom type symbol saying that this is an oxygen. And also we use a standard, although seldomly used, atom site attached hydrogens data item, where we say that, yes, although we don't know the coordinates, we know that there are 2 hydrogens next to it. So if your software is prepared to handle this, in the new revision, you get a better data, more accurate material representation. I'm very happy to tell you that our users also contribute to the creation and improvement of the crystallography open database. So Thomas Dortmann from Panalytical Company, he needed mineral identification for their customers who use crystallography open database, and he complained that our mineral names are sometimes wrong, sometimes formulas are given there. People publish all sorts of different descriptions for this, not standardized. So he just took all our collection and sent us a file where he said, entries that have mineral name are minerals, the rest are not. And since that time, 3,500 minerals are correctly identified, and then later we upgraded this to more than 4,000. So everybody can contribute, and it's really a good collaboration example. As said, all our data are versioned, and every change is committed as a separate revision. You can access them using standard subversion tools, which I will show in a while, but you can also access them on a website. If you go to an endpoint with just a crystallography open database identifier, you will get the latest revision of the record. But if you append the revision number, then you get exactly the same bit stream of data that existed in that particular revision. And I think this is very important for reproducibility of your data and for traceability of the results obtained from the crystallography open database. If you look at how to obtain the code, you will see the description of methods with some commands cited, and you can download the whole database to your computer. It's done with svn checkout command, and here I would like to show you one trick which I find especially handy, because crystallography open database become larger over time, and it's getting still larger, so it takes some space on your disk, and not all things are necessary. If you are not going to start up the website, then you don't need the web software and all the tests, and which can be quite large. So you can give option depth empty, and when you check out working copy, you will get just an empty directory, and then you can update to the infinity depth just those branches or those directories that you are interested in. The CIF branch contains coordinate data for all structures that we have. HKL data contain FOBS data for some of them. SME contains SMILES, chemical identifiers, for those materials which we identified as chemical molecules. And if at some stage you decide that you no longer need some of them, you can set the depth to exclude. So quite handy, we are using that. You can not only download the data from the crystallography open database, but you can also deposit it through this web links and the deposition system. We have created a very simple but I hope usable deposition system that guides you through the steps necessary to collect all data. It also helps you to get missing data items. For example, the bibliography data for a published structure can be inserted automatically if you know DOI, and the full bibliography will be inserted into your ZIF file online, because this is a required information for published structures. And when you do all things right, you get this green page where deposit to the COD button can be pushed, and then you get the new COD identifier assigned. To maintain data quality, we do several checks, and the first layer and the strictest layer, but the simplest at the same time, are syntactic checks done by ZIF parse. So we make sure that all data that come into crystallography database are syntactically correct according to the definition of the International Union of Crystallography, and this enables massive automated processing of that data. Okay. We then start doing semantic validations against ZIF dictionaries to make sure that data items have correct syntax and correct units, and they are internally consistent. And I gave more examples of that during my Monday's talk, so you can grab slides and see some more detailed examples here, which I'll skip for time. And then finally, we do database-specific checks to make sure that the rules that we and the advisory board set for the crystallography database are satisfied. And not only the advisory board, but we also follow recommendations of the International Union of Crystallography. So if you make personal communication to the COD, and we are the only entity who checks the quality of the data, then ZIF check will report if there are some issues with quality criteria on the in the submitted file. And if you get this during the deposition, then you have two options. Either you refine your structure better, and sometimes this is possible, I experience it myself, or you just contact us and explain why this is not possible, why this is okay, which is, for example, sometimes the case with electron microdiffraction structures. We are working to update this criteria, and also the grand vision is that in the future we will have an automatic structure review website where not only the advisory board, but all the community can come in as reviewers and say their expert opinion on particular structures where they are acceptable for you, because that's for your use or not. We support 3 types of deposition. You can deposit a published structure, which comes from a journal supplementary data. In that case, it must have the full bibliography, or at least a DOI, and we assume then that it's peer-reviewed already, so we don't insist or enforce the IUCR quality criteria, assuming that the reviewers did their job. There can be a pre-publication structure, which are going to publish in a journal, but the publication is not yet out. So you get the COD ID, but the data are on hold, not exposed to the public. Default is 6 months, but this is extensible. Here the IUCR checks are performed and enforced, and again, if something is wrong, we get in contact and discuss that. And in this case, only cell constants, space group of your crystal, and the chemical composition, the summary formula are published so that everybody knows that you solved this particular structure, but all other data, including coordinates, are kept confidential, and they are only become public when the publication is out or when you yourself release that data. Finally, you can deposit structure as a personal communication using crystallography open database as a sort of journal to publish your data. It becomes public immediately, and IUCR checks are performed and enforced. Now, when you have this amount of data, of course, again, maybe I make an insertion. On Monday, people asked, what is the benefit of contributing to the crystallography open database. And I mentioned some benefits, but I think I forgot the most important one, so I use the opportunity to say it. You see, when you have an organized body of information, it has much more value than a single set of than your single record. Okay, you solve the structure, and immediate questions arise. Did somebody else solve structure for the same molecule or material? Is it in the same space group? Maybe it's polymorphic. What other molecules has it been co-crystallized with? And if you have all the previous records, you can immediately answer those questions, or you at least have a means to answer those questions. If not, then all bets off. And so those people who have access, who have this data collection, they are really at benefit. So if you contribute to an open database, this benefit immediately comes back to you. You put in your single structure, and you get 500,000 of others with which you can compare your work, and you can plan your future work. So I think that it's a win-win situation for everybody. Okay, for most of the community, let's put it this way. If your business plan is based on making data scarce, then of course you might be at a disadvantage, but I think we can come to terms with that. Okay, so then we have all this collection. We can now derive chemical information, the chemical entities of the molecules that are inside the crystals. And we have done this. We take a symmetric unit of a crystal, we restore molecules using symmetry operators of the crystal, resolve disorder, which is also important. And then Antanas Vaitkus wrote software for interpretation of or chemical feature comprehension. He determines bond orders, charges, hybridization types, and tautomers, the hydrogens of the molecule. And with this information, we can now link our database with chemical databases, such as PubChem, and we can generate chemical identifiers, INCHI or SMILES, that can be used for searching, for identifying materials. And this all data is available in several formats, SDF, CML. You can download it all from the website cited in this paper, or you can use the software that Antanas has created to calculate them yourselves. So this is the flow information. This enabled us to donate some 200,000 entries to the open PubChem database, and they conveniently identify where we are here. And this is the example of one of these entries that is generated based on the crystallography open database. So by comprehending chemical information, automatically deriving it, we can now tell what the chemical entities are in there, and from here you can learn all chemical parameters like protonation constants. You can even find who sells this compound, if you are interested in repeating the experiment. It's not only the PubChem that, okay, it's actually already mostly done, yeah? It's not only PubChem that we are trying to link our database with. We have links to MCSD, Wikidata, Wikipedia, MPOD, and ChemSpider. And most importantly, we plan to soon roll out links to raw data. Raw diffraction data, which is now stored in several archives like XRDA or protein diffraction. For this, we use a very simple method, but it turns out to work. For each external database, we have a separate data table in our SQL database, which has external identifier, the code identifier, and the relation ID. So far, the only relation we use is these two records have something in common. It's very, very broadly defined, but of course we can introduce any other relations and actually build on existing ontologies. And from this you can automatically generate links, and since you can make SQL queries, you can join SQL data table with these tables and get the results programmatically. To maintain crystallography open database, and here come to the last point of my talk, to software, we need software, quite a lot of it, some of it we write ourselves, and we want to make sure that our software is as bug-free as possible, relevant to this conference, I hope. So I was looking for tools that would enable me to check all aspects of correctness of the software. And I'm very enthusiastic about the Spark system that allows me to formally specify how the software should behave in a mathematical way, and then there are tools that attempt and sometimes succeed to prove that what you have coded indeed satisfies the post conditions and the definitions of your code. So here, for example, I define what it means to be a crystallographic symmetry group, or just mathematical group. Okay, as you know, it must be closed on multiplications, all elements must have inversions, and to be a group, you must have an identity and these two properties. And of course, has identity was defined before. So the good thing about Spark system is that it allows you to do in the same code, which can, on one hand, be run through the prover, and then it says whether your post conditions are proved or not. Okay? On the other hand, you can compile it, okay, and then you can run exactly the same code which you have proven to pass the prover checks. Okay? And the underlying language for this is Ada, and I would like to share some of my experiences with it. It's new in the sense that it's well forgotten old. Designed in '83, but the latest standard is 22. It's actively developed. It's mostly backwards compatible, so if you have code from 30 years old, it's a useful library, you plug it into the modern compiler, and it just compiles and runs, pretty much like C does. You can plug in Kernighan-Ritchie code into the GCC from the last year, it compiles and runs. Okay, it's statically very strictly typed, has a rich type system, so it catches a lot of errors at compile time. Nowadays we have a good open source compiler, not available. If you are using GCC, then you are just one step away from taking benefit of the system, because it's in the same compiler collection. Rich type system, it has language level concurrency. If you want 20 threads, you just say, I want 20 threads, and you get tasks carried out. In parallel, optimizes and generates native code and is not controlled by any private company. There is an ISO standard for that. So why are not we programming in Ada? It's such a good question. And in '97, there was even a research procured by the Department of Defense to do this. To investigate this, and they came to the conclusion that language is very useful for their purposes, but it's complex and difficult to implement. So back in the last century, there were no good compilers. Admittedly, I tried it. It was procured by Department of Defense and used for warfighting software. So I wouldn't be surprised if HIMARS has a software written in that system. And as a result, maybe due to some pacifist feelings, it was not very well represented in academia, and then students don't know it, and they don't bring it to industry. So that was last century, but I think nowadays most of these considerations are no longer valid. There is a good compiler. So the fact that language is difficult to implement is no longer an obstacle. In fact, we can say it's a rich language that allows us to express our ideas and let the compiler check if we did this correctly. No good compilers, no more relevant. The GNOT is really doing a good job and generate code. At least as good as for the G++, for the GCC. Yes, it's still used by the Department of Defense, but it's also used in many peaceful applications, such as avionics, spacecraft control. So Ariane 5 was programmed in Ada, and maybe you know this infamous failure of Ariane, but if you look at their track record, this is one of the most reliable launcher systems, turns out. Most of their launches are successful. It was just one or two that were. And if you go back by Airbus, then chances are that your pilots are using computers programmed in Ada. So, and Spark allows formal verification of the code, which is very important for those guys, but if it's good for Airbus, why shouldn't we use it for science, for crystallography, for beamlines, for databases, okay? Because we deserve good software. That would be my, my call. And the poor academic outreach still stays, but I mean, I'm trying to rectify that. This is an example of some code which I wrote just to see how this works. This is interpretation of crystallographic Hall symbols, where you take a formal space group description and generate space group operator for that. So to me, this looks like a pseudocode, right? And I would say it's pretty readable, never mind the deep nesting level, because we can have very high-level abstractions. You define what is a symmetry operator. This is a type, okay? You say that n is positive, and then you just multiply the operators. You can define these operations in a formal way. Pretty much like several modern languages do, but this was available in '83. Okay, and then you compile that, and it turns that this test program is very handy. I'm using it daily, actually, to figure out what the symmetry operations are for a specific space group in the crystallography open database, because these Hall symbols are not very readable. So to conclude, open data, crystallographic data are useful, important, so let's get more of that. Everybody's welcome to contribute, so let's collect more structures. Let's use the best available tools to make reliable, bug-free software, and maybe ADA and Spark are some of these tools. Maybe they could be learned. And yeah, your contributions in all senses are very valuable and welcome. And I am indebted to many people who collaborate with me, with whom I collaborate, and who collaborate with me. This is my team in Vilnius. And this is the advisory board of the Crystallography Open Database. Enormous thanks for our commercial supporters, Panalytical, Rigaco, and Brooker, and acknowledge funding of Lithuanian Research Council and Vilnius University Intramural funding. Thank you for your attention. The slides are there. Below are the slides with the references, in case you would like to fetch the papers or the code that I have mentioned, and I'm ready to take questions.
Okay, well, thank you. I think a lot of it's interesting to see we got a solution for having no bugs now. Yeah, so we go to other.
Well, that we would like to say this, but I think I was careful enough not to claim bug-free software. Yeah. You can still make bugs, for sure. Just the question is how much your tools support you in catching these bugs as soon as possible. So the ADA will not compile your program if it has type mismatches. Okay. Now, we all know that type mismatches are bad, so if you program in dynamic languages and you have type mismatches, then you have a runtime error. Now, in ADA, you will have a compile time error in most of these cases, so you learn the problem much, much earlier, and the compiler even gives you a hint how to rectify it. They could say, well, this is the wrong type, but probably it's a misspelled this and that type. Okay, or you should make a typecast from that type to this because they are compatible, but you should be explicit. Yeah.
No, I think it's very interesting, and I was wondering, is there anyone else using ADA in the audience?
Okay, no hands. That's
so there's still a lot to go, yeah. But
yeah, well, I'm curious what will be in a couple of years.
Yeah. Are there any questions? Yes, Jérôme.
Hi. Thanks for this very inspiring talk. Huge work has been done. I'm a bit concerned, and I'm wondering if you deliberately stick to SVN, or if you consider switching to Git. Are your tools too much integrated with SVN? Because I didn't play with SVN for 10 years now, and to my souvenir is that it was quite slow and really. And if you're considering to moving to other version control system,
okay. So the short answer is no. The more elaborate answer is, I think SVN is good enough, and in some senses it's better than Git. First of all, it's a centralized system. Now, if you do a bazaar-style software development, maybe that a decentralized system like Git is better. Maybe, I say, because in all projects which I observe, they collapse to a centralized model. You have a central repository, which is an authoritative source of code, and then you either commit there or you make pull requests there. So, I mean, it's centralized anyway. Then what Subversion allows to do us, it allows us to version timestamps. And this is important because timestamp is an important part of data provenance, and you can check out with the commit timestamp, not with the checkout timestamp. And Git notoriously, Linus Torvalds notoriously refused to introduce this feature, saying that this is a nonsense and nobody needs it. And yes, I agree, for software development you don't need it, but for data management this is a very useful feature. And finally, Subversion is simpler to use, and I know it well. It works excellent. So if it ain't broke, why should we fix it? Okay. So it does all the necessary features. It's actually extremely reliable. So now I can say, in 25 years, I haven't lost a single revision through many hundreds of thousands. Okay, we had 5 repository corruption or so repository corruption events due to failed hardware, which we could restore from backups. So I think it's amazing stability. With Git, I have already, in a couple of years playing with it, I've already lost some of my code because, oh, you just made a wrong, how it's called, rebase, yeah, the wrong rebase, and your revisions are gone, and you vacuum, and oh gosh, okay, it's bad luck. So in this sense, conceptually, Subversion is simpler, and I think in some senses simpler is better. Now, regarding being slow, well, it is slow because it needs, for many operations, a connection to the centralized server, but that's not inherent to the Subversion itself. It's the network connection that limits us. However, I mean, this is a compromise, and on the other hand, in Unix, if some operation is slow, you just shift it to background, and if you need to check out the crystallography open database for the first time, yes, it can take a couple of hours, maybe, so you leave it overnight, and that's it. And the next morning you have it, and then you do updates, which you will need to do to pull in Git anyway, so the network will be in your way, and the updates are very fast, just seconds. So that's why I recommend the SVN checkout of the Subversion.
Thanks a lot. And regarding cybersecurity then, because if you have a central point, central repository, of course you have backups, but it makes it also more vulnerable to cyber attacks. Maybe wrongly directed, but...
do you mean the code itself?
No, not the code, but
or in general, the centralized model?
Well, in general, the centralized application is that if the SVN server gets corrupted, well, if you have backups, you can restore. But
yeah. So we have backups, of course. We do daily backups. Then we have, well, we had 4 offline, offsite copies in different countries. Now, I must admit that at the moment, one in Granada, managed by Miguel Quiros, is operational. Others are, due to lack of manpower there, not updating anymore, but we have at least one offsite backup. The vision is to make equal peer system where would be more than one server, and this is perfectly doable with the Subversion itself, because logically, it's a centralized system, and you commit to one place, but you can have passive mirrors, and these mirrors can switch dynamically. My student did his master and demonstrated that this is possible. Unfortunately, it's not yet ready for production rollout, but yeah, we are thinking on that.
Thanks a lot. Let's just check the time. I think we still got time for a few more questions. Anyone? I have a few if you don't. Yeah, there's some more. Yeah.
I was wondering, how is the funding model looking for COD now?
Good question. So it all started by the researchers mentioned before, taking out their pocket money, buying servers, and universities providing internet connectivity and electricity. And this runs to, this is also still relevant now, so that's why I'm very grateful to intramural funding of the Vilnius University, because Vilnius University supports, gives us servers. We have a rack space in the Tier 2 data center, so it's really well maintained from the hardware point of view. Then we apply for grant funding, and our research is mostly concerned with data management, using of data, like deriving chemical data. So part of the grants are dedicated to maintaining the crystallography open database, which we need for our research, and then we're happy to share it with everybody. And finally, I'm very happy to announce that last year Vilnius University approved the open science guidelines and implementation guidelines, and they acknowledge the importance of open science infrastructure. So there is a chance that the crystallography open database will get dedicated funding, just necessary to keep it afloat, not because we do new science, which we do, try to do, but not only for that, but also for maintaining, for keeping the infrastructure running. It's not a big money, I mean, you can do it in your garage if you need, but of course the help from the state and from the university would be very helpful. And I must admit, also, not admit, I must tell also that commercial users also give some support in terms they give us hardware, they support us financially as much as they can due to their internal restrictions and policies. So these are the funding sources.
So you talked about Ada. What about Pascal, which is a descendant of Ada and had a lot more success in academia and industry back in the day?
Excellent question. Well, first it's the other way around. Ada is the descendant of the Pascal, and I would say Ada is Pascal on steroids. Now, there is an interesting paper actually published by Department of Defense from, quite old paper, which said we switched in our, it was a military school, from teaching students Pascal. We teach soldiers to program. So they switched from Pascal to Ada, and they claim this was a success. Okay, we usually, when you write a paper, you claim it to be a success, but it's doable. Now, my personal experience is that I gave an opportunity for my students this year to program in Ada instead of other languages which they knew for bioinformatics, and I was amazed that in one semester they came from not knowing the language into writing a fully functional code, with my help, of course. I had to show many things, but they were enthusiastic about that. They managed to understand the logic of the language, so Ada is very learnable. Okay, should we? So now Pascal obviously had very serious limitations. You probably know them: fixed array sizes and bad packaging and so on and so forth, which made it largely unsuitable for large software development, although people tried. And you probably remember I think it was Brian Kernighan who said, why Pascal is not my favorite programming language. Okay, there is a paper or a post by him where he explains the deficiencies of Pascal. Now, in my view, and I'm ready to defend it, ADA fixes all of them and introduces a lot of more conveniences. So the reasons why Pascal is not an industrial language, I don't advocate in writing things in Pascal, I think these considerations are not relevant to ADA.
Okay, one last question. Maybe from me, I was wondering what message, because everyone here is coming, most people are coming from a large infrastructure or, like a synchrotron or a neutron source. How can we help, the COD in the sense of, is there any activity that we should be?
Well, definitely you can use it. Start using it right now. For example, if your users solve a structure, you can just run a check and see if that's to index a crystal, and you run a check, and you see if that's in the COD or not. As I also showed before in the Monday talk, there is a programmatic way to deposit structures. So you could give your users an opportunity when they solve the structure, deposit it as a pre-publication. For example, what is the benefit for the users then? Well, they have their data accessible and confidential as long as needed from anywhere in the world, and then when they need to publish it, they just grab the ID and put it into the paper. So that could be a really very close collaboration between the facilities, the structure solvers, and the
there's also a large activity to store raw data. So we could also be linking the raw data.
Absolutely.
To the.
I hope we will have this raw data links working by the end of this year.
Okay.
So a person needs to be hired next week who will do that.
Okay, I think we hit the time limit, so thanks once again for an excellent talk, Saulius.